Hello everyone, I am Rajita Dak and I am going to explain you about simulation race condition in RTL design. What is RTL design? RTL stands for Register Transfer Level and its description is the lower level of abstraction than the behavioral description but higher level abstraction than the netlist description of the circuit design. In RTL description, circuit is mainly described in terms of registers, that is flip-flop and latches, and the data is transferred between them using logical operations or combinational logic if needed. And that is why its name, register transfer level. RTL description is written using either Verilog or VHDL. It is the first real dig at the detailed circuit design and all the subsequent steps in the IC design process depends upon the quality of the RTL design. User first starts with designing of the block. After the design of the block, that is by describing the functionality of the block in the form of RTL, the RTL code is then synthesized. Synthesis is done to realize the gate level connectivity that would provide the same functionality. But before synthesizing, the designer needs to ensure that RTL actually implements the desired functionality or not. For this purpose, the designer runs a lot of simulations which shows for a given set of input vectors what would be the response. These input vectors are supposed to cover various situations like normal mode of operation, specific corner case situation, error or recovery handling, etc. Simulation is certain till the time the RTL has only one possible interpretation, but there are situations where some pieces of RTL code can have multiple interpretations. If the designer gets satisfied with the exhibited functionality, it is possible that during simulations the interpretation used in different form what gets finally realized, that is synthesized, and if this happens then even after simulations are verified the device does not exhibit the same behavior. Now next comes the simulation race. What does simulation race means? In the context of HDL simulations, the word race means some HDL code exhibiting two or more behaviors and both of which are correct as per the language implementations. Race implies ambiguity, that is uncertainty, as simulators are free to choose from among different interpretations. This condition is mainly encountered in Verilog code. In case of design having a race, different simulators can give different results. Different version of same simulator can give different results. Same version of same simulator can give different results based on the components used. Now next comes the different conditions due to which race occurs. First is the read-write race. Read-write race occurs when a signal is being read at the same time as being written into. Considering this example, A is written through the assign statement while being read through the always block. While B gets updated, it will trigger both the assign statements as well as the always block. The if statement in the always block will see the updated value of A if the assign statement is executed first. On the other hand, the if condition will see the old value of A if the always block get executed first. Depending upon which of the two behavior is chosen by the simulator, we might get different behavior. Thus, this code segment represents the race condition. In order to remove these race condition, the sensitivity list of the second always block should have A in it. This will ensure that as soon as A gets updated, the second always block gets triggered and values are re-evaluated with the updated value of A. In the worst case also, the second always block might get triggered twice, but final values would be unambiguous. Second is the write-write race condition. Write-write race occurs when multiple values are being written into a signal at the same time. Considering the following code segment, as we can see that as B changes, both the always block gets triggered, and it is possible that in one of the always block, error flag is supposed to take the value of 1, while in the other it is supposed to take the value of 0. The value that flag finally takes will depend on the sequence in which these always blocks gets triggered, and the one which triggers later will determine the final value. Race is being created because of the assignments in the two always blocks made to same signal. Solution to avoid this ambiguity is to avoid updating a signal in more than one concurrent block. Write-write condition occurs through the combination of first assign statement and second always statement. But when these conditions are used in design, this will result in multiple driver scenario after synthesis. Now next condition is always initial race condition. Always initial race condition occurs when the initial block is updating a signal which also appears in the sensitivity list of the always block. Consider the below code segment. Let us consider two different conditions. Scenario 1. Always block is triggered first. So now it has to wait for the positive edge of the clock or the negative edge of the RSTN. So it now waits for the triggering event to occur. After that initial block is triggered, which causes RSTN to set as 0, thereby causing negative edge on RSTN. Since the always block was waiting for negative edge of the RSTN, it starts executing, taking Q to D. Let us consider another scenario in which at the start of the simulation, initial block is triggered first. It takes the RSTN signal to 0, which means that negative edge on the RSTN has already happened even before the always block could wake up and is missed by the always block. So Q does not get initialized at the start of the simulation and always block will wait for the next event to occur. Thus the simulator might exhibit any of the above behavior. This kind of places is resolved by using some inactive values and then initializing after a while. This has been shown by modifying the code segment. In this, at first, RSTN is initialized by any value so that it will trigger the always block. Now we will talk about different conditions for avoiding simulation race. When modeling sequential logic, we use non-blocking assignments. When modeling ledges, use non-blocking assignments. When modeling combinational logic with an always block, use blocking assignments. When modeling both sequential and combinational logic within the same always block, use non-blocking assignments. Do not mix blocking and non-blocking assignments in the same always block. Do not make assignments to the same variable from more than one always block. Use strop to display values that has been assigned using non-blocking assignments. Do not make assignments using zero delays. Thank you.